Hello, good morning everybody. I welcome you all to this series of lectures in EDC, Electronic Device and Circuits. I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering, IARE. Today I am going to discuss about the diode resistances and the equivalent circuit. So there are three categories of resistances of the diode. They are DC or static resistance, AC or dynamic resistance, and average AC resistance. So these are the three types of resistances: DC or static resistance, AC or dynamic resistance, average AC resistance. So the basic diode equation is I is equal to I naught into e power v by eta vt minus 1, where I is the current passing through the diode and I naught is the reverse saturation current at the room temperature and V is the external voltage which is applied to the diode. That means it is a voltage across the diode, across the two terminals of the diode, positive and negative. And eta is a constant and it is 1 for germanium and it is 2 for silicon. And Vt is equal to Kt by Q, or we can say Vt is equal to 11,000 by T by 11,600. And K is the Boltzmann's constant and Q is the charge of electron, which is 1.6 into 10 to the power minus 19 coulombs. And T is the temperature of the diode junction. And at room temperature, Vt is equal to 26 millivolts. So, the temperature dependence of VI characteristics. See, the current through the diode, it is the function of temperature. As the temperature increases, the number of charge carriers, holes and electrons in the diode, they increase and the resistance of the diode it decreases and the current through the diode it increases. So the reverse saturation current I naught of the diode it increases as we increase the temperature. So approximately it increases at 7% per degree centigrade for both germanium and silicon. So as 1.07 to the power 10 is equal to 2, we can say that the reverse saturation current doubles for every 10 degrees rise in temperature. For example, if for 30 degrees centigrade, if the reverse saturation current is 30 nanoamperes, if the temperature is doubled to 60 degrees centigrade, it doubles to equivalent value. So if at 30 degrees centigrade, if the reverse saturation current is 30 nanoamperes, if we increase the temperature to 60 degrees centigrade, the current also doubles to 60 nanoamperes. So the reverse saturation current, it approximately doubles for every 10 degrees rise in temperature. So if the temperature is increased at a fixed voltage, then the current I also increases. So to bring I naught to its original value, what is to be done? The voltage across the diode has to be reduced. So if we keep the voltage across the diode at a fixed value, but if we increase the temperature, naturally the current through the diode it increases. But in case we want to make the current constant, though the temperature has increased, what is to be done is the voltage V has to be reduced. The voltage V across the diode has to be reduced. Now, the temperature effects of the diode are graphically represented in this figure. So, you can see here, as the temperature increases, the curves they shift towards the left side. Next, for germanium, the very important reason is that the silicon devices they enjoy a significantly higher level of development and utilization in design, because the thermal stability of silicon is much better compared to the thermal stability of germanium. In germanium, the outermost valence electrons are there in the fourth orbit, whereas for silicon they are in the third orbit. So the valence electrons are under the tight grip of, by the nucleus in silicon compared to the germanium. So silicon semiconductor is more stable. So the increasing levels of temperature account for the lower levels of threshold voltage. So if we increase the temperature, the threshold voltage it reduces. Now let us say what are the different types of resistances in the diode. First is the DC or the static resistance. So the application of a voltage to the circuit which consists of the diode will result in current. So it results an operating point on the characteristic curve that will not change with the time. So the resistance of the diode operating point can be found by simply finding the levels of VD and ID. So for example, this is the characteristic VI characteristic of the diode. So this is the operating point Q. Okay. So at this operating point Q, the voltage is VD and the current is ID. So what is the DC resistance at this operating point Q? The DC resistance RDC is equal to VD by ID. For example, if VD is equal to 0.8 volts and ID is equal to, let us say, 80 milliamperes, then RDC is equal to 0.8 divided by 80 milliamperes. So that is equal to 0.8 by 80 K. So that is equal to 10 ohms. Yeah. So as we move across this characteristic curve, we get different values of resistances. So this is called the static resistance. Suppose if we move the operating point to this place, here we have more current and almost the voltage remains constant. So here at Q2, we are going to have less resistance because the current is more. Similarly, suppose if you come to this point Q3, here current is less and voltage is more or less same like Q or Q2. So in this case, at point Q3, we are going to have more DC resistance. So we can say that the resistance at RQ3 is greater than RQ, and that is, and resistance at RQ is greater than RQ2. Okay, so this is nothing but the DC or static resistance. So we assume that there is a fixed voltage that is applied to the diode, and the fixed voltage is constant. So we get a constant current flowing through the diode, and the constant current can be determined by using the characteristic curve. So this is if the diode is forward biased. So when the diode is forward biased, we get more current. So the resistance is going to be less. Suppose if we apply the reverse voltage to the diode, that is called the reverse bias. So practically no current flows. We can say that the diode offers a very high DC resistance. Now coming to AC or dynamic resistance, if instead of DC voltage, if AC voltage is applied to the diode, then we are going to have not a constant current, but the current also is going to vary. So if a sinusoidal rather than DC input is applied, we are going to have a varying current. So when the current and voltage, when they vary, they result in varying resistance. So that is called as AC or dynamic resistance. So with we assume that when AC signal is applied, already there is going to be a fixed DC voltage, there is going to be a fixed operating point, and around that operating point, the AC signal or AC voltage variation is going to be there, resulting in variation, sinusoidal variation of the current. So this is going to cause the variation of resistance, and this variation resistance is called as AC or dynamic resistance. So the designation Q point is derived from the word quiescent. So it is also called still or unvarying. So Q point corresponds to the DC operating voltages where the current and voltages are fixed. So when AC signal is applied, we are going to have variations around this Q point, resulting in the dynamic resistance. So if you see here, this is the VI characteristic of the diode is like this. When the diode is forward biased, so this is the voltage and this is the current I. Now this is the operating point Q. Now if we have to find out the AC or dynamic resistance around the point Q, then we have to draw a tangential line and we have to find out the slope of that, and the inverse of the slope of the tangential line will give us the AC or dynamic resistance. So this is the Q point. So here let us take this small this one point we are going to take, this another point we are going to take, and this the difference between these 2 points will give us delta VD, the change in the voltage across the diode, which is going to cause change in the current to the diode. So this is delta ID. So the dynamic resistance RD is given by delta VD by delta ID. So AC or dynamic resistance, we assume that the variations in the signal is less. For small variations of voltage across the Q point, we are going to decide or we are going to calculate the AC resistance. That means for small swings of operating voltage around the Q point or around the quiescent point will give us the AC resistance. This is also called as the dynamic resistance. And what is the ideal or diode model? So the ideal or diode model, you know that when the diode is forward biased, it is going to cause more forward current. It allows large amounts of current. And when the diode is reverse biased, practically we get very less current passing through the diode. So we assume that the diode acts like a switch. That means when the diode is forward biased, it acts like a closed switch. So this is a diode, and we are applying the positive VD. That means the diode is forward biased. So and we are going to have large amounts of current. So this will it is similar to the switch being closed. And when the diode is reverse biased, so the VD is in the reverse polarity, and there is going to be a very less current passing through the diode, and the current is nothing but the reverse saturation current, which is of the order of microamperes for germanium diode and which is of the order of nanoamperes for the silicon diode. So the current to the diode is almost zero. It is almost zero. So For positive values of VD, we are going to have large amounts of current, and for negative values of VD, the diode is switched off, or the diode is in off condition. So when the diode is forward biased, it's like a closed switch. When the diode is reverse biased, it is like a open switch. So this is the ideal diode characteristic. But in reality, the diode is there is going to be a non-linear relationship between the voltage and current. We are not going to have the linear relationship, but we are going to have non-linear relationship in the practical diode. So for most applications, the resistance average is sufficiently small to be ignored compared to the other elements of the network. So the removal of RAV from the equivalent circuit is same as implying that the characteristic of the diode appears as shown in the figure. So the reduced equivalent circuit appears in the same figure. It states that the forward biased silicon diode in an electronic system under DC conditions, it has a drop of 0.7 volts across the conduction state at any level of diode current. So when the diode is for a silicon diode, when we apply a forward bias, the current through the diode starts to flow when the applied voltage is more than the cut-in voltage. For silicon, the cut-in voltage is 0.7 volts. So when the applied voltage is more than 0.7 volts, then only the diode conducts. So the practical diode, it can be represented in this way. This is the ideal diode with which has just now I have shown you the characteristic with this type of characteristic. This is the ideal diode with no cut-in voltage. But the practical diode has some cut-in voltage, which is the 0.7 volts for silicon and 0.2 volts for germanium. So what happens? The practical diode can be represented using this circuit where 0.7 volts voltage source is in series with the ideal diode. So for the current to pass through the diode, we have to apply a voltage which is more than 0.7 volts. So this is the circuit for the semiconductor diode which has some cut-in voltage. Now, piecewise linear equivalent circuit. The other technique for obtaining equivalent circuit for the diode is to approximate the characteristic of the device by straight line segments, and the resulting equivalent circuit is naturally piecewise linear equivalent circuit. And it is obvious that the straight line segments do not result in exact duplication of the actual behavior. So, this is a piecewise linear circuit. We have assumed for simplicity that the characteristic is like this, but the relation between the current and voltage is non-linear in a practical diode. It is not straight like this, it is somewhat like this as shown in this figure. So, the piecewise linear equivalent circuit is like this, and it has some slope. So we have discussed about the DC or static resistance, which has a fixed value of resistance because the applied voltage is constant and the resulting current also is constant. So that gives rise to DC or static resistance. And AC or dynamic resistance, it is as we discussed, the AC or DC is equal to delta V by delta I. So, we assume that the swings which are applied to the diode are very small, resulting in relatively large swings in current that gives rise to AC or dynamic resistance. So, here you can see the applied swings, voltage swings are small, and the resulting current swings are high. So, for small swings of applied voltage, the AC or dynamic resistance is calculated. And for average AC resistance, we assume that the applied voltage has large amounts of variation as shown here. So here delta VD is small, here you see delta VD is more. So this causes similar large variations in the current. So we get more value of, we get a different value of resistance, and that is called as average AC resistance. So these are the three types of resistances which we are going to take into account when designing circuits with the diode. Now let us discuss about the breakdown mechanisms in semiconductor diodes. So in semiconductor diodes, there are two mechanisms of breakdown. One is the avalanche breakdown and other is the Zener breakdown. And these breakdowns, they come into picture when the diode is reverse biased. So in avalanche breakdown, the minority carriers under reverse bias conditions, they acquire a kinetic energy which increases with increase in the reverse voltage. So when sufficiently high reverse voltage is applied, the charge carriers, they gain a high momentum and they attain very greater speeds, and they go and hit the atoms when they travel through the diode. So this releases the valence electrons from the clutches of the nucleus, and more charge carriers, they become available for conduction. So suddenly what happens? Large amounts of current, they flow through the diode. So as a result of this collision, the liberated electrons in turn liberate more electrons, and the current becomes very large, leading to the breakdown of the crystal structure. So this phenomena, it is called as the avalanche breakdown. So this avalanche breakdown, it occurs in the conventional diode. And the Zener breakdown, it is another type of breakdown which occurs in the Zener diode. So in Zener diode, the junction width is small because of high doping of the P and N regions. So under a very high reverse voltage, in such case, the depletion region, it expands and the potential barrier increases, leading to a very high electric field across the junction. So this electric field, it will break some of the covalent bonds of the semiconductor atoms and leading to a large number of free minority carriers, which suddenly increase with the reverse current. So this is called as the Zener effect. So the breakdown occurs at a particular and constant value of the reverse voltage, and this is called as the breakdown voltage. So this Zener breakdown, it occurs at an electric field intensity of 3 into 10 to the power 7 volts per meter value. So these are the Zener breakdown, it occurs at the lower value of applied reverse voltage, and avalanche breakdown, it occurs at high value of applied reverse voltage. And in Zener diodes, the breakdown voltage has less, the slope is, the curve is very steep. More or less, it gives a constant voltage. Whereas in avalanche breakdown, the current has a characteristic is something like this. So the current voltage is not going to be constant. So this is the characteristic of Zener diode, and this is a characteristic of conventional PN junction diode. Okay. Now let me summarize about what all I have discussed in today's class. So there are three types of resistances: DC or static resistance, AC or the dynamic resistance, and average AC resistance. So the DC resistance, it is due to the fixed value of DC voltage, which results in fixed constant current, and AC or dynamic resistance is due to the small variations in the applied AC voltage. And in both cases, and in AC dynamic resistance, we assume that already there is a fixed amount of DC voltage which causes Q point or quiescent point. And for average AC resistance, we assume that the large swings of applied voltage are present. And this is a diode current equation. I is equal to I naught into e power v by eta vt minus 1, where eta is the constant and eta is equal to 1 for germanium and eta is equal to 2 for silicon. And Vt is the voltage equivalent of temperature, which is nothing but kT by Q. Or this also can be calculated as T by 11,600. And K is the Boltzmann constant and Q is the charge of electron, which is approximately 1.6 into 10 to the power minus 19 coulombs. And T is the temperature of the diode junction. So at room temperature, Vt is equal to 26 millivolts. So the reverse saturation of the current, it is a function of the temperature. So as the temperature increases, the reverse saturation current, it increases approximately 7% per degree centigrade for both germanium and silicon. And as I have told, suppose let us say at 30 degrees centigrade, if I naught is equal to 40 milliamperes, then if the temperature is increased to 60 degrees, if the temperature is doubled to 60 degrees centigrade, then it becomes 80 milliamperes. So the reverse saturation current, it doubles for every 10 degrees rise in. The reverse saturation current doubles for every 10 degrees rise in temperature. So for if the temperature rises, sorry, not 60, if the temperature rises to 40 degrees centigrade, then it becomes 80 milliamperes. Suppose if the temperature is raised to again to 50 degrees centigrade, then this becomes 160 milliamperes. So if the temperature is increased at fixed voltage, the current I also increases. So to bring the current to its original value, the voltage V has to be reduced. So these are the temperature effects on the diode. As the temperature increases, the curves they shift towards the left side, causing more values of current. So DC or static resistance we calculate at any point on the characteristic curve. We take the value of the corresponding values of VD and ID, and RD is equal to VD by ID. Suppose you want to find out the DC resistance at this point, then you take the value at this point V1 and you take the value of current I1 at this point. So then R1 is equal to V1 by I1. And let us say you want to find out the DC resistance at this point, then you take the value voltage V2 and what is the corresponding value of current I2. So R2 is equal to V2 by I2. So as the curve is not linear, the DC resistance, it varies as we move across or we move as we travel through the characteristic curve. So different points on the characteristic curve, they give different values of DC resistance as depicted here. And AC or dynamic resistance, as I have already explained you, we take what is the variation current for small variation in the applied voltage. So those two things we note down, and the AC or dynamic resistance RD is calculated as delta VD by delta ID. And there is another way of calculating the AC or dynamic resistance. How we calculate is like this. You know the diode equation is like this. I is equal to I naught into e power V by eta Vt minus 1. So dou I by dou V is equal to I naught into e power V by eta Vt into 1 by eta Vt. So this is equal to I plus I naught into divided by eta Vt. So this is approximately, as the reverse saturation is negligible compared with the actual current flowing through the diode, we can say that this is equal to I by eta Vt. So dou V by dou I is equal to eta Vt by I. So this is nothing but the resistance or the dynamic resistance. So this way also the dynamic resistance can be calculated. But if there are going to be large variations in the applied signal, then we use a different term that is called as average AC resistance. Okay, that average AC resistance we calculate like this. So you take this point and you take this point and join these 2 points and find out the slope of this line, and the inverse slope of that will give us the average or the average AC resistance. And the ideal diode model, if we neglect the cut-in voltage, it is represented in this way with zero cut-in voltage. And but actually we are going to have the cut-in voltage, which is 0.7 volts per silicon. And if we take into account the cut-in voltage of the silicon diode, then it can be represented in this way. So the characteristic curve is going to be like this. But in piecewise linear circuit, what we do, the characteristic curve we don't it is going to be somewhat like this. This is VD and this is ID. And in this case, the diode is going to be represented in this way. A small amount of forward resistance, then a small DC source which represents the cut-in voltage, and then ideal diode. So this is a representation of practical diode or equivalent circuit for the practical diode. So this is RF. So this RF will take care of this slope. Okay, and this voltage VF will take care of this cut-in voltage V gamma, and this is the ideal diode. So this, in summary, these are the three resistances. This is a DC or static resistance at this Q point, and AC or dynamic resistance. We take these 2 points, and for AC or average resistance, we take these 2 points which are at more distance. And we have discussed about 2 types of breakdown: avalanche breakdown and the Zener breakdown. Avalanche breakdown, it occurs in conventional diode for higher voltages, and more reverse voltage is applied. That is going to increase the speed of the charge carriers, and they attain greater velocity, and they go and hit the adjacent atoms, liberating more and more charge carriers, so thereby increasing or causing large values of current. So that is the avalanche breakdown. And Zener breakdown, it occurs in the Zener diode, and for relatively small values of applied reverse voltage. So with this, I conclude today's session on the diode resistance and equivalent circuits. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.